Hello, welcome back. We are on chapter 22 of Materials Kinetics, which is an introduction to molecular dynamics simulations. What I'd like to do today is to give you all the basics of what goes into doing a molecular dynamics simulation and how we can calculate properties, including kinetic properties, from MD simulations. We're going to start today with kind of an overview of materials modeling at different scales, so we can see what are the other techniques available for doing materials modeling and how does molecular dynamics fit into that bigger picture. Then we will go into some of the details of MD simulations, including interatomic potentials, the use of different ensembles, some of the key principles of MD simulations, including how to integrate the equations of motion, and then we will get to calculation of macroscopic properties. So let's start with materials modeling. One of the great things about materials science is that we can study it at many different scales. If you look at the smallest possible scale, this would be the electronic level that studies the details of how electrons interact with each other to form various types of bonds within a material. This also relates back to optical properties, electrical conductivity, and other dielectric properties. And this is done at the quantum mechanical level. So the finest, smallest length scale for doing materials modeling would be at this electronic level using quantum mechanical simulations such as density functional theory or Moeller-Plesset perturbation theory. If we were to take kind of the next coarser level of granularity here, instead of considering each electron to be the most basic particle, if we consider each atom as the most basic particle, now we're no longer in the realm of quantum physics, we're back in the realm of classical physics, and there we have atomistic simulations. This lecture, we're going to be focused on one type of atomistic simulation, which is molecular dynamics simulations. In the next chapter, we will deal with Monte Carlo, which is another way to do classical atomic scale simulations. But we don't stop there. If we go to kind of the next coarse grain level, we can look at the microstructural evolution in materials. So things like phase field modeling, which we covered in a previous chapter on phase separation, that can be used to help model the evolution of microstructures in materials and connect that back to materials properties. And then, of course, at the greatest length scale, we have macro scale simulations. That could be looking at the entire part. So the length scale here could be meters or so. And this is normally the domain of mechanical engineering rather than material science. As material scientists, we normally focus on these other three levels here: electronic, atomistic, and microstructure. So what is molecular dynamics? Molecular dynamics is a classical atomic scale simulation technique for calculating the structure and properties of materials. These simulations are performed by integrating Newton's second law of motion, F equals ma. This second law of motion here, F equals ma, provides the foundation for everything that we do in molecular dynamics. And everything else is basically how to do this as accurately and efficiently as possible for a large system of atoms. Now, within MD simulations, each atom has its own position. So it has its own position vector, which would be its x, y, and z coordinate. And it also has a momentum vector or a velocity vector with the x, y, and z components of either the velocity or the momenta. And what MD does is by integrating F equals ma, we update the positions and the velocities of the particles over time, and then use those trajectories to calculate the properties of the material. So taking an overview of MD simulations, there's a set of input that we need to provide in order to perform MD simulations. The most basic input is, of course, the composition of the material. What are the different elements involved? How many atoms of each type of element are in the material? We also need to provide a starting configuration of atoms. This could be maybe a known structure, like a known crystal structure, or it could be randomized placements of atoms if you're doing a liquid structure. But we need to provide like how many atoms of each element and what are their starting configurations. We also need to specify the interatomic potentials in the MD simulations. The interatomic potentials govern the interactions between atoms, and those are what's used to calculate the forces acting between atoms. We also have to specify the ensemble, which means, is this, say, a constant volume simulation or a constant pressure simulation or something else? We have to choose boundary conditions. So do we have periodic boundary conditions or not? And we need to choose the time step of the simulation and how long the simulation will run for. So this integration of Newton's equations of motion, that occurs by integrating over time. So we need to specify an appropriate time step and then the total time to run the simulation. Now, after doing this and running the MD simulations, the output is an atomic level description of the material structure. So this would be the detailed positions of all the atoms as a function of time. And from that, one can calculate properties such as the radial distribution functions, bond angle distributions, coordination numbers. You can do beautiful visualization of material structures. So basically, every structural property is available to you. And you can also perform property calculations as a function of time, including mechanical properties, thermal properties, kinetic properties, and so on. Now, the ability to conduct molecular dynamics simulations rests upon having an accurate description of the interatomic potentials. These are the energetics that are associated with atomic interactions. Now, in principle, we can expand the total potential energy of a system following this cluster expansion approach, where if this V here is this fancy calligraphy V is the total potential energy of the system, that potential energy of the system would be a summation of all the one-body potential energies. So this would be all of the energies that are associated with the atoms themselves. So that is, all of the interactions between the electrons within an atom, all the interactions between those electrons and the nucleus. Then we would have two-body interaction terms. So this is doing a double summation over all pairwise combinations of atoms. And this V2 then is a function of the separation distance between atoms, Rij. And we will have functional forms that describe those interactions. You could continue and do a nested summation of three summations here to get three body potentials. These would depend upon the separation distances between two pairs of those atoms and then the subtended angle between them. You could have a torsional term that has four body interactions here, which depend on three radii, two bond angles, and one torsion angle phi. And this continues. And in principle, this continues all the way up through nth order interactions, where n is the total number of atoms in the system. Now, the reason we do expansions like this is that the importance or the magnitude of each of these terms becomes less and less as you go to higher and higher orders. So by far, the greatest amount of energy is actually in the one-body term. This one doesn't actually contribute for classical molecular dynamics simulations because it's the same as a function of time. We've got the same number of atoms of the same type. What we're doing with MD is not studying the interactions within the atom because the atom itself is the basic unit. What we are studying are the interactions between atoms. So this one-body term, even though it's the largest contributor here, this is not considered an MD simulations because of the atom being the fundamental unit. So this does not change within MD simulations. It's not calculated within MD simulations. You would need to go to a quantum mechanical approach to calculate that. So instead, with MD simulations, the most important term is actually this pairwise term, this pairwise interaction potential, which governs the potential energy interacting between every pair of atoms. Um, in many MD simulations, maybe even in most MD simulations, that's all we have. It's just these pairwise interactions. Um, but some MD simulations also incorporate angular terms, and those angular terms are incorporated through a three-body interaction here. And that is typically much smaller in magnitude compared to the two-body pairwise interaction. And then there are some systems, especially polymeric systems, that may have torsional terms as well. And this would be, of course, even smaller in magnitude compared to the three-body bending terms. So to summarize, most MD simulations just have this two-body term. Sometimes you might also have a three-body term and occasionally also a four-body term. Now, this is an example of what one of these two-body interatomic potentials may look like. The points here show the potential energy as a function of interatomic distance that were calculated through quantum mechanical simulations. So the points here are the ab initio calculations from quantum mechanics, and then the solid lines are fits to those data using the functional form here shown in this equation. And this is what's known as a Morse potential. It has a well depth here, D0, which governs how deep this potential energy well is. A deeper well, of course, would be a stronger bond. There is this R0 parameter, which governs the equilibrium separation distance between atoms. And then there's the shape parameter alpha, which governs the shape of this curve. So this Morse potential is often used to describe covalent interactions in materials. And this is convenient because we're taking these very complicated quantum mechanical results here and describing it with a functional form, which has only three fitting parameters, D0, alpha, and R0, and is just a simple function of one variable, the interatomic separation distance here, Rij. And you can see that this classical potential in this case gives a very good representation of the quantum mechanical results, so we can use this with confidence. And in many cases, this might be the only potential that we would use. However, if we wanted to include a three-body interatomic potential, what we would need to do there is to isolate out the angular contribution by taking the total three-body potential, subtracting out all the two-body contributions, and then what's left is the angular contribution. And this is an example of that shows the potential energy of what's left of this tellurium-tellurium-tellurium interaction calculated from quantum mechanics as a function of bond angle theta. And then you could assume different functional forms for this three-body interaction. In this case, it's assumed to be this function is given by with a separation of variables, that there's a product of radial pieces here that depend just on the separation distances, and then an angular piece, which just depends on the subtended bond angle theta. The radial component decays here. This is just chosen as a hyperbolic secant function. And then the angular component, in order to capture all these wiggles, is given by a Fourier cosine series. So this is just an example. There aren't as many standard functional forms for three-body interactions compared to two-body interactions because A, they're often not needed at all, and B, the shapes often don't follow some standard form. But whatever the interatomic potentials are for the system, those need to be defined, and they need to be provided as input for the simulations. The next thing that you need to decide is the choice of ensemble. And what I mean by this is the statistical mechanical ensemble that is used in the MD simulation. The most basic type of ensemble and kind of the default ensemble for molecular dynamics simulations is the microcanonical ensemble, also known as the NVE ensemble. The microcanonical ensemble is an isolated system with constant volume. Because it's isolated, that means that the number of atoms are constant, so N is constant. Also, the internal energy of the system, E, is constant. And then because it is constant volume, we have V here as well. So that's why the microcanonical ensemble is also known as the NVE ensemble, because N, V, and E are held constant during the course of the simulation. Now, one of the things that we know from Newtonian mechanics is that if we are integrating Newton's equation for motion, that is energy conservative. In other words, potential energy gets converted to kinetic energy, which gets converted back to potential energy, but the total energy of the system is a constant. And therefore, if all we do here is solve Newton's equations of motion, the total energy of the system is constant. And by default, then, pure molecular dynamics, if you don't have anything else added to it to change anything, just molecular dynamics in its native state is by default in the microcanonical ensemble. Now, most of the time, for practical cases, we don't have a constant internal energy, but rather we have a constant temperature. This is if your system is somehow coupled to some thermal reservoir that keeps a constant temperature of the system. And this is more typical in experiment because we usually control the temperature of the system. And so kind of the more common way to do MD simulations is in this canonical ensemble, which is closed, meaning that it has constant N, isochoric, meaning that it is constant volume V, and isothermal, meaning that it has a constant temperature T. And the way to do canonical ensembles, as we will see, is to incorporate a thermostat in the MD simulations. A thermostat is what will control the temperature of the system, and it does so by periodically rescaling the velocities of the atoms to maintain that constant temperature. So even though microcanonical ensemble is the default case in MD, the more common way of running MD is in the canonical ensemble. And in fact, probably most MD simulations are conducted in the canonical ensemble. We can take this a step further and go to the grand canonical ensemble. Here, it's still constant volume and constant temperature, but it's an open system rather than a closed system. So the grand canonical ensemble is also known as the mu-VT ensemble because instead of having a constant N, we have a constant chemical potential mu. Now, grand canonical simulations are usually done using Monte Carlo simulations, and I will explain how those are done in the next lecture and the next chapter in the book. Because with Monte Carlo, basically you can add atoms and subtract atoms from the system more readily. There are other ensembles that you could choose from. There is an NPE ensemble, which would be an isolated system with constant pressure. This would be a fairly rare thing to use. One that is a lot more common is the NPT ensemble, which is a closed isobaric isothermal system. So for the NPT ensemble, it's kind of like the canonical ensemble, only instead of having a constant volume, we have a constant pressure. And this is used rather often because it does represent experimental conditions in many cases, because many experiments are conducted under constant pressure conditions rather than constant volume conditions. So NPT is also rather common to use. It's probably the second most common ensemble to use after the canonical ensemble. And here we still use a thermostat to maintain the constant temperature, but then we also need to include a barostat in order to maintain the constant pressure of the system. And then finally, one final ensemble is the mu-PT ensemble, which is also known as the Gibbs ensemble. And this has a constant chemical potential, a constant pressure, and a constant temperature. This is usually used to calculate phase equilibria, usually in the context of Monte Carlo simulation. So this is something we will revisit next time. But right now, I just want to point out that one of the key differences between MD and Monte Carlo is the default ensemble, or kind of the native ensemble of the technique. With MD, because it is solving Newtonian mechanics, it is going to assume by default that the energy of the system is constant, and therefore, by default, it is a microcanonical ensemble. With the Metropolis Monte Carlo technique, this is based on sampling and using a Boltzmann distribution. This, by default, is in the canonical ensemble. And so this is actually one of the key differences between MD and MC, where MC is by default in the canonical ensemble. It doesn't need a thermostat to maintain that constant temperature. Now, how do you choose which ensemble? In order to apply statistical mechanical techniques, including MD simulations and Monte Carlo simulations, we need to choose an appropriate ensemble for the system under study. And that choice of ensemble depends on the state of the system and its surroundings and the desired thermodynamic properties to be calculated. So the way to figure this out is to see, what are you trying to represent? What are the realistic experimental conditions for that system? Is it something that's being done at constant temperature, or is it something that's being done under constant volume or pressure? And based on that, you can choose the appropriate ensemble for your simulation. Other times it's governed by what properties you want to calculate. So for example, the thermal expansion coefficient would be kind of most easily calculated in the NPT ensemble because of the definition of the thermal expansion coefficient, which is a change in the volume of the system with respect to temperature for constant N and for constant P. So what you would do here is to conduct NPT simulations, allowing the volume of the system to change by keeping the system at a constant pressure, and then conducting those simulations at different isothermal conditions to see how the volume is changing as a function of temperature under constant pressure. So the NPT simulation, NPT ensemble would be the most natural choice for those simulations. Now, what do we need to do next is integrate Newton's second law of motion. So this is really the crux of MD simulations, is that we are going to generate successive configurations of the system by integrating Newton's second law of motion. And the result of this calculation is a trajectory that specifies how the positions and the velocities of the particles in the system evolve with time. And this is all based on using Newton's second law, F equals ma. And what we have here is if we divide both sides of this equation by m, what you can see is that we've got the acceleration here on the left-hand side of the equation. The acceleration is the second derivative of the position with respect to time. And then that would be equal to the force that is acting along that direction. So if this is the acceleration for xi, this would be the force acting along that xi direction divided by the mass of that particular atom, m sub I. How do we do this? As we've done several times already in this class, we're going to do Taylor series expansions. What we have here first is a Taylor series expansion of the position at a new time. So if we've got the initial position here is at the position r at time t, the question becomes, what is the updated position of the atoms after propagating the system forward by a time step of delta t? So what is r at t plus delta t? We do that as a Taylor series expansion starting with the initial position, so r of t, plus then the time step, delta t, times the first derivative of the position with respect to time, so that is the velocity function, plus then 1 over 2 factorial, so 1/2 times the time step squared, delta t squared, times the second derivative, which is the acceleration. Then we've got 1 over 3 factorial, the delta t cubed, times the third derivative of the position, which would be the derivative of the acceleration, which is usually labeled as b. So this would be b of t. And the word for this, the name for the derivative of the acceleration, is the jerk. We can also do a Taylor expansion of the velocity in the same way, where this is starting with the velocity at the initial time t. Then we've got delta t times the first derivative of velocity, which is the acceleration, plus 1/2 delta t squared times the next derivative, the jerk, plus 1/6 the delta t cubed times the next derivative. So this would be the fourth derivative of the position, which is c of t. And this fourth derivative of the position is called the jounce, or also called the snap. And if you keep going, you can keep taking derivatives. The next derivative with respect to time would be d, and that is actually called the Krekel. And the next derivative after that, the e function, is called the pop. And I'm not making this up. Those are the actual names. So this position, first derivative is velocity, second derivative, acceleration, third derivative, jerk, fourth derivative, snap, fifth is crackle, and sixth is pop. So there we go. Now we want to calculate our acceleration. Now, what we need to do to apply F equals ma is to calculate F. We need to calculate the force acting on each atom in the system. That force is the negative gradient of the potential energy. So if we take the gradient of our total potential energy function, the force is acting downwards, so it's acting down the gradient. So F equals minus the gradient of the potential energy function. Then the acceleration vector here, this acceleration vector A, is simply the force divided by m. And so this becomes minus the gradient of the potential energy function divided by m, and that's what gets us the acceleration vector. Now, one of there are various mathematical techniques to perform integration of the F equals ma function to get the updated positions and velocity vectors. The most basic of these algorithms is called the Verlet algorithm. This is a widely used method for integrating the equations of motion. This uses the positions and accelerations at the current time t and the positions from the previous time step to calculate the new position. So the way that the Verlet algorithm works is that you've got this Taylor series expansion at the next time step. So this is R of t plus delta t. And this is given by the Taylor series expansion shown here, where we are going to truncate after the quadratic term. So it's R of t plus delta t times the velocity, plus 1/2 delta t squared times the acceleration, and then we truncate. Now we're also going to have the equation here for the position at the previous time step. And now taking this position from the previous time step and doing the same type of Taylor series expansion, this is equal to R at the current time, now minus delta t, because we're going backwards in time, minus delta t times the velocity, plus 1/2 delta t squared. Notice that the minus delta t, when that gets squared, that's still positive, times the acceleration. Then what we need to do is add these two equations together and solve for what the position is at the new time step t plus delta t. And so adding them together, you can see that these velocity terms cancel out because they are the same thing, except this one is positive and the same term in the next equation is negative. So these velocity terms exactly cancel out. And what we have on the right-hand side is 2 times the current position, 2 times R of t. Then we're going to bring this R of t minus delta t to the other side of the equation. So it's minus the previous position. And then plus, we've got these two terms here are identical for the acceleration term. So these are, we've got a 1/2 delta t squared a and another 1/2 delta t squared a. So this becomes just delta t squared a. So with the Verlet algorithm, the position at the new time, so R of t plus delta t, is equal to twice the current position minus the previous position plus the time step squared times the acceleration. And that is like the most straightforward way to update the positions in MD. And one of the advantages or disadvantages of this technique is that it bypasses calculation of velocities. This is an advantage in the sense that it is being very efficient computationally, but it's a disadvantage because in many cases, we actually do want to know the velocities. We may want to know the velocities to calculate certain properties, and we definitely need to know the velocities if we want to maintain a constant temperature simulation. So if we are doing a simulation in the canonical ensemble or say the NPT ensemble, and we want to maintain a constant temperature, we have to know what those velocities are as a function of time so we can rescale the velocities to keep the same temperature. So a modified version of the Verlet algorithm is known as the velocity Verlet algorithm. And this is useful because it provides not only the positions as a function of time, but also the velocities as a function of time. So the velocity Verlet algorithm gives positions, velocities, and accelerations without compromising on precision. And the way that this works is that we've got a similar Taylor series expansion of the position at the new time that is truncated after the acceleration term. And then we also have a Taylor series expansion of the velocity at the new time step. And this is represented as the current velocity here, v of t, and then plus the delta time step times an average velocity at the current time and the new time step. And so this average velocity is the a of t plus delta t divided by 2. And we use this average velocity then to give a more accurate prediction of what the velocity will be at the next time step. The challenge here is that it requires acceleration at the subsequent time step, so a of t plus delta t. So the method for implementing the velocity Verlet algorithm is as follows. First, we calculate the new positions according to this equation here. So this is r of t plus delta t equals r of t. So the current position plus delta t times the current velocity plus 1/2 delta t squared times the calculated acceleration, which was calculated, as I showed you before, just minus the gradient of the potential energy function divided by the mass of the particle. So this gives us our updated position. Then we calculate the velocities at a half time step. So this is going forward by just a half time step, 1/2 delta t, and the velocity at that half time step forward would be equal to the current velocity plus the half time step times the acceleration. So it's plus delta t over 2 times the acceleration. Then new forces are computed from the current positions, from these new positions here at t plus delta t. So now we've got this new acceleration here at a of t plus delta t. And using that new acceleration based on this new position, then we can get the final velocities. And so taking the velocities all the way to the end of the time step, that is v of t plus delta t. So now we're going all the way to the end of the time step, and that's equal to the velocity of this half time step, plus then taking the next half time step. So it's delta t over 2 times the acceleration at the new time step. And so this is effectively using the current acceleration for the first half step, the final acceleration for the second half step. So it is effectively giving an average acceleration to take the full time step forward. Now, what are some of the considerations for these integration algorithms? Ideally, the integration algorithms should be fast, accurate, and require minimal memory. The integration algorithm should conserve energy and momentum. It should be time reversible because Newton's equations of motion are time reversible, and it should permit as long of a time step as possible to be used, because if you can use a longer time step, then you can access longer time simulations, but only if you can do that accurately. So how do we choose a time step? There's no hard and fast rule for calculating the most appropriate time step. If the time step is too small, then you're going to spend way too much calculation time and only cover a limited time, so only explore a limited portion of phase space. On the other hand, if the time step is too large, then you will get numerical instabilities in your integration algorithm, and that will lead to violations of energy and momentum conservation. So that is a very serious problem. Typically, for most MD simulations, the time step is on the order of a femtosecond. So it's on the order of 10 to the minus 15 seconds. These are very small time steps in order to ensure the accuracy of the MD simulations. And that's why MD simulations are primarily limited by the timescale that they can access, because if you're taking time steps on the order of a femtosecond, it takes, say, 1 billion time steps in order to reach a microsecond in your total simulation time. So that's why one of the biggest disadvantages of MD simulations is how constrained they are with respect to the timescale. Now, with all of these background all this background information in place, how do we initialize our MD simulations? We need to establish an initial configuration of atoms and initial velocities of the system. The initial configuration can be obtained from experimental data, from some perfect crystal model, maybe random distributions of atoms. Whatever it makes sense for your initial positions of atoms, you need to specify that in the MD simulations. So that's the initial positions. How do we get the initial velocities? They are obtained based on the temperature of the system. And this would be the initial temperature of the system, and randomly drawing values from a Maxwell-Boltzmann distribution to get the momenta that corresponds to that particular temperature. So this is the probability of having velocities at different levels. And then this is a function of the mass of the particle, the temperature of the system, and then this would give the Maxwell-Boltzmann distribution. So this is our probability density function, and we need to draw a random value for each of the velocities along each of the x, y, z directions for every particle in the system. So based on this temperature of the system, we randomly draw these values and randomly assign the velocities. If you have higher temperatures, on average, the velocities will be higher. The next question is boundary conditions. The MD simulation operates based on a simulation cell, which is basically just a box. And it's the box where you contain your atoms, and it's the box where all the action takes place. If you don't do anything, if there's no boundaries, then these atoms could float off in space. You could have a rigid boundary, in which case that's like having a rigid wall where the atoms would just bounce off the walls. But what's more common is to specify periodic boundary conditions. And this is especially more common in materials science, where we usually want to model extended materials, so not just isolated molecules. With periodic boundary conditions, what we assume is that if an atom leaves one side of the simulation cell, that it will re-emerge on the opposite side of the simulation cell. So for example, this purple atom here, if this leaves through the right wall, it's going to come back and re-enter on the left-hand side. So this simulation cell is defining the repeat unit in the MD simulation. And what this means also is that the atoms can interact not just with each other within the same simulation cell, but with these periodic images of each other. So for example, if we were to pick, say, this purple atom here and this atom here on the other side of the simulation box, it looks like a really long distance between the two of these if you just look within this simulation cell. So it looks like that maybe they wouldn't interact very much with each other. However, there is a periodic image of this atom on the other side here, and the shorter distance is actually between this atom and this periodic image. So when we do periodic boundary conditions, we need to consider not just the atoms interacting with each other with the positions defined within this simulation cell, but also all periodic images of each other. And it's also important to make sure that the simulation cell is large enough so you don't have artificial interactions of like an atom interacting with a periodic image of itself in across one of these periodic images. So it's important to make sure that the simulation cell is large enough so that doesn't happen. Now you can have periodic boundary conditions in all three directions. That would be appropriate for a bulk simulation. If you are simulating a surface, you can shut off the periodic boundary conditions along one direction in order to create a free surface. So it might be periodic, say, just along 2 dimensions with an open surface along that third direction. How do we calculate some kinetic properties? One of the most basic ones is, of course, the diffusion coefficient. And we already know from our Einstein equation for diffusion that for a 3-dimensional system here, we would have our 3 times the diffusion coefficient is equal to our mean squared displacements of atoms divided by twice the time. So what we calculate from the MD simulations is the time trajectory of these positions. So what we're calculating is the R of t with respect to the initial positions. So all of this position information is there in the MD simulations. And if you calculate this for a long enough time to ensure convergence of the results, then take that mean squared displacement, divide by, in this case, would be divided by 6 times time. That would give you the diffusion coefficient in 3 dimensions. So it's actually a rather straightforward calculation using MD simulations. Another way that this can be evaluated is based on the Green-Kubo formula. This is based on a velocity autocorrelation function. So it's keeping track of, instead of the positions, how the velocities are evolving and how the velocity at some time tau correlates with the initial velocity at time 0. And then integrating that from the initial time 0 to some current time tau. And how that velocity correlation function evolves governs or is related to the mean squared displacement of atoms. So this is an alternative way to get at the diffusion equation. And we will study more about the Green-Kubo formulation in a later chapter in the book that deals with fluctuations in condensed matter. Okay, now, what about thermostats? How do we calculate the temperature of the system? At any point in time, the instantaneous value of the temperature is related to the kinetic energy via the particle's momentum. So if this is the kinetic energy of the system, capital K, if we've got the square of the momentum divided by 2 times the mass of that atom, this summation here gives us the total kinetic energy of the system. And this is our thermal energy here, kT over 2, times the number of translational degrees of freedom in the system. So this would be 3n, where n is the number of atoms, because every atom is an x, y, and z degree of freedom, minus this n sub c, which is the number of constraints, or the number of ways that the system can be moved that don't correspond to thermal vibration. So this is typically a number like 6, because you could take the entire simulation cell, move the entire simulation cell in the x direction, move it all in the y direction or all in the z direction, and where you could rotate it along 3 different axes. And those are all modes of motion that don't contribute to the vibrational thermal energy. When n is large, as it usually is, this minus nc doesn't really matter, because the n would be so much larger than this nc. So in effect, it becomes 3/2 nkt to get that kinetic energy. Now, if we want to do the simulations under constant temperature conditions, we need to go from the default of the microcanonical or NVE ensemble to the canonical ensemble or NVT ensemble. And the simplest way to do this is with a thermostat that rescales the velocities every so many time steps. And that scaling factor here is given by lambda, and that is equal to the square root of the required temperature over the actual temperature of the system. And what this means is that we have a target temperature that's required. This is where we've set our thermostat. If the temperature of the system, after integrating Newton's equations of motions, if the temperature becomes too high because we've converted too much potential energy into kinetic energy, then we would rescale the velocities downward in order to achieve that target temperature. They're all rescaled by this constant factor of lambda. If the temperature becomes too low, then we would scale the velocities higher in order to, again, achieve that temperature that is required here, this T required. In either case, we're rescaling the velocities of all the atoms by the same constant here, lambda. Now, what if we have an NPT ensemble where we have an isobaric simulation instead of an isochoric simulation? In that case, we need to calculate the pressure of the system as well as the temperature of the system. The pressure in MD simulations is usually calculated using the virial. The virial is defined as the expectation value of the sum of the products of the coordinates and the particles and the forces acting on them. The total virial consists of an ideal gas part, which is shown here, and a contribution due to the interactions between particles, which is this second term. And the virial theorem here states that this virial, which has the ideal gas contribution and the contributions due to the interactions, is equal to minus 3 nkt. And then what we need to do is, in order to maintain the constant specified pressure, we adjust the volume of the system to maintain that pressure. So the volume can either expand or contract in order to maintain the constant pressure. So if you've got an NPT simulation, you'd be calculating the temperature, rescaling the velocities to maintain that constant temperature every so many time steps. For the constant pressure part, you'd be calculating the pressure using this barostat, and then rescaling the volume to maintain the constant pressure. So a macroscopic system maintains constant pressure by changing its volume. A simulation in the isothermal isobaric or NPT ensemble also maintains constant pressure by changing the volume of the simulation cell. A volume change can be achieved by changing the volume in all the directions or just one direction as appropriate for your system. And the procedure for maintaining constant pressure is then analogous to that for maintaining constant temperature. Now, one of the cool things about MD simulations is that we can get not just average values of properties, but also fluctuations in properties. And those fluctuations relate back to macroscopic properties. And we've got a whole chapter on that, about that later in the book, the chapter on fluctuations in condensed matter. But just as a sneak peek, if you, for example, you have the average here of the squared variation of the total energy of the system. So if you take the Hamiltonian of the system and look at the squared fluctuations of the Hamiltonian, they relate back to the constant volume heat capacity. So the CV here can be calculated from this variance of the fluctuations in the Hamiltonian divided by KT squared. That gives you the constant volume heat capacity. And this is done in the canonical ensemble. If you do the same thing in the NPT ensemble, but calculate the enthalpy and look at the variance of the enthalpy fluctuations, that divided by KT squared gives you the constant pressure heat capacity. So these fluctuations can be used to get macroscopic properties that we care about, like the heat capacity. Another example is the thermal expansion coefficient. And the thermal expansion coefficient can be calculated by this cross-correlation of volume fluctuations and enthalpy fluctuations in the NPT ensemble. So if you look at this cross-correlation of volume and enthalpy fluctuations divided by KT squared volume of the system, that gives you the volumetric thermal expansion coefficient of the system. And what this is telling you is that if the volume and enthalpy fluctuations are correlated together, like maybe always increasing the enthalpy, little positive fluctuations in enthalpy also correspond to positive fluctuations in volume, that's indicative of a high thermal expansion coefficient. If you wanted to have a negative thermal expansion coefficient, then there would be some anti-correlation between volumetric and enthalpic fluctuations, where if one goes in one direction, the other goes in the other direction. We can also calculate any structural properties that you can think of using MD simulations because we know the positions of all the atoms at all points in time. For example, the pair distribution function here shows you how likely you are to find an atom at some position R with respect to the center atom here at position 0. So if you start off at a central atom here at position 0 and you go upward in R, there'd be a 0 probability of finding an atom because they don't like to be overlapped with each other because of Pauli's exclusion principle. But then when you get to the first nearest neighbor shell, there would be a peak there, and then another peak for the second nearest neighbor shell, and so on. So these pair distribution functions, which show you how atoms are positioned relative to each other, can be calculated for any system. I also want to point out that more advanced MD simulation techniques exist where the interatomic potentials can vary depending upon the local environment of atoms. And two of the leading researchers in the field here are right here at Penn State. Dr. Susan Sinnott is the developer of the COMB reactive force fields, which are most suitable for modeling systems with a combination of different bonding types. Like if you've got a system with metallic bonds and hydrogen bonds and covalent bonds, um, in the same atom might experience different types of bonding depending upon its local environment. With these reactive force fields following this comb method, those particular potentials are going to change depending upon that local environment. Another one of the leading researchers also here at Penn State is Professor Audrey Van Duyn. He is the developer of the REACTS-FF reactive force fields. And these are especially tuned for giving accurate calculation of reaction pathways. So if you've got chemical reactions happening in your system, REACTS-FF is a way to actually follow that entire reaction pathway and get accurate energetics along the pathway. So these are more advanced types of MD simulations. This shows you an example from some of Susan Sinnott's work. This is the spreading of a water droplet on metallic copper. So you've got the copper substrate here. These are water molecules on top. So you've got two different types of bonding, metallic bonding within the copper, hydrogen bonding here within the water, and the interactions between the water molecules and the copper themselves. And you can see how this is the bird's eye view here. This is the drop of water on top. This is the cross-sectional view, and then zooming in, you can see the individual water molecules and how they are reacting with copper and how they are spreading up to copper. So it's a really great way to see, to visualize exactly what is happening at this atomic scale. Here's another example from Susan Sinnott's work. This is a titanium carbide derived carbon that has carbon as well as titanium carbide in there, and having some rather complicated microstructures here with different types of bonding. And with these reactive potentials that she and her group have developed, she's able to get both of those types of bonding. This is an example from my group, a assistant research professor in my group, Young Zheng. He did simulations using REACTS-FF, using Audrey Van Duyn's reactive potentials that show how this metal organic framework called ZIF4, which is a zeolitic imidazolate framework. It is a metal organic system, so it's a combination of different types of bonding in that as well. Starting off with a crystal here, and then heating it up into the liquid state, and then quenching it down into the glassy state. And you can get the atomic level details here of what the crystal looks like, what the liquid looks like, and what the glassy state here looks like. Now, there are lots of tools available for doing MD simulations. Two of the most popular tools are LAMMPS and GROMACS, and both of these are available here. And there are also a wide variety of visualization tools to make those beautiful images. Some of them that are quite popular are VMD. So VMD and Ovito are probably two of the most popular right now. Atom Eye is another really good one that comes from Professor Ju Lee from MIT, and XKristen is another one. So please, check out some of these websites if you want to try running MD simulations or visualizing some of these results. So to summarize, MD simulations solve Newton's equations of motion for atoms with a defined set of interatomic potentials. The ensemble and boundary conditions should be chosen according to the problem that needs to be solved, and the accuracy of MD simulations depends on the accuracy of those interatomic potentials. All right, next time we will go to Monte Carlo simulations. So thank you very much, and I will see you then.